So last week we studied about resolution of forces, how we take one force and resolve it into two elements, the vertical and the horizontal element. And then the week before we learned about resultant force, which is taking two or more forces and then combining it to find one single resultant force. All right, so all of that, we will be using that in this one. Let's just read this first chapter. Photograph 1.4 shows a ngajat dancer standing still for a while during a dance. So if you have your textbooks, you can see there's a picture of a dancer staying still. So what is the relationship between the forces acting on the dancer? Since the acceleration of the dancer is zero, there is no resultant force. Therefore, the forces are said to be in equilibrium. So an object is said to be in equilibrium when the forces acting on it produce a zero resultant force. So we learn how to find resultant force. But if all the resultant forces add up to produce zero, then we say that that object is in equilibrium. Okay? For example, we have a picture of a vase standing still on a table. The weight of the vase is 12 newtons, and the weight of the reaction in the opposite direction is sorry. There's something. Sorry about that. Okay. Where was I? Weight of the vase is 12 newtons going down. The reaction, normal reaction on the vase is 12 going up. So if we were to find the resultant force, and we can do it using this, resultant force, reaction is going up is 12 newtons, weight going down is 12 newtons, we end up with 0. So when you end up with 0, this is what we call a state of equilibrium. That's all that equilibrium means. Now, take note, just because something is in a state of equilibrium does not necessarily mean it is standing still. Okay, tidak semestinya benda yang berada dalam keadaan equilibrium bukan bermaksud dia tidak bergerak. Kadang-kadang dia bergerak juga, because even in this description here, dia tidak katakan the speed of the dancer is 0, but it only says the acceleration of the dancer is 0. So, kalau satu objek itu berada dalam state of equilibrium, when an object is in a state of equilibrium, that either means either the object is static or is staying still. That's one. Or object is moving at a uniform speed. So these are the two possible situations where an object could be in a state of equilibrium. Sama ada dia dalam keadaan pegun, ataupun dalam keadaan bergerak dengan hal laju tidak berubah, a constant speed. So if we have two directions, two forces, then the calculation is quite simple lah. Yeah, you have up and down or left and right, and both forces are the same, just in opposite directions. It gets a little bit more interesting when we have three forces in three different directions. So you have a lamp here, and going to the right we have 3 newtons. Going down, we have the weight of the lamp itself, which is 4 newtons. And then we have another piece of rope going up at an angle, letter T, at 5 newtons. And the lamp is not moving, so the lamp is in a state of equilibrium. So for this one, we use something called a triangle of forces. So if we just have two then we can just use a normal diagram up and down or left and right. When we have three forces to consider, then we have to draw a triangle of force like this one. Now, keep in mind that the triangle, the sides of the triangle might not look exactly like what is in the picture. However, the direction of each side will be the same. Okay, so let me just show you something, how we can get the triangle and how the triangle actually shows us the resultant force is 0. So what we do, well, let's start with let me go back to so we start with whichever force we have. So we have W, P, and T. So we can start with W. So W, so for W, we draw a straight line going down, just like in the graph. So that's W. And then we go on, we go to the next direction, which is T. So, sorry, not T, P. So let's go ahead and draw T. P, sorry, which is 3 newtons. So W is 4 newtons. P is 3 newtons. And last one we have is T. So T being 5 newtons. So in this situation, it forms a right angle. For a triangle of forces to be accurate, all of the arrows must be pointing none of the arrows should be pointing at the same corner, right? So the direction needs to go from sort of like you're going around in a circle here. So this one points to this one points to this one, that one points at that one. Okay, so if you have a triangle of forces and you draw it like this, then you have a mistake somewhere. You cannot draw your triangle of forces like that. So how is it that this is showing equilibrium? How does this picture show equilibrium? How does this picture show the resultant force is 0? Well, if you remember what we learned last week about resolution of forces, we can actually take this line here. So let me just move this line over here. Let's say we took this line and we move it here. 5 newtons. We can actually resolve this into two forces. Remember what we learned last week? We take this, we turn it into a vertical and a horizontal aspect. So Fx and Fy. Actually, it shouldn't be F, it should be T. Now, notice this very carefully. The horizontal aspect of line T is going in the opposite direction of W. And the vertical is going the opposite direction of W. The horizontal aspect of Tx is going the opposite direction of P. So P will cancel out Tx and W will cancel out Ty. And even without counting, I already know that they're equal because they are in equilibrium. So that's how you can, that's how this triangle is actually showing that there is a resolution or there is a resultant force of 0, because this line actually represents two forces, or we can consider it as two forces. So one force cancelling this one force cancelling this one, or producing a resultant force of 0. So when we do questions, one of the things that we usually do in questions is we use the resultant force. No, not the resultant force. We resolve one of the sides into two forces to calculate the other two sides. Let's continue. And if you're not sure what I'm talking about yet, later when we do the examples, it will become clearer. Okay, just for now, just make sure that we can make a triangle of forces. So let's take a look at a few situations here. Let me just zoom into this picture just a bit. That's a bit too much. So let's look at a few different situations and let's look at how we can make a uh, triangle of force for these different situations. So the first one, we have a box basically sitting on a slope and it's standing still. And we have 3 arrows. So for this one, it's quite easy. It's just do it the same as the one that we did before. So W going down. So let's start with that one, W. So let's take the line W. And then the next force is Fr, or friction reaction, frictional force. So we'll just connect. We'll just continue the triangle. And then we have the reaction force, so R. And so let's just continue the triangle. And this produces a 90-degree angle. So when it produces a 90-degree angle, the calculations are easier. But sometimes it might not always be 90-degree angle. Okay, so as long as all your arrows are just basically going in, it continues from one direction to another. What might be a little bit more interesting is when you have a situation like this one, like question number 2 here. So for example number 2, you have T. We have 2 sides letter T, which means they're equal. And we have a W pointing down. So at first glance, you might think that you're supposed to draw it like this. Okay, kung nampak ada triangle dalam gambar, so either you might think, okay, begini, T and W. Alright, well that's not correct, obviously. So what you do, start with W again. Alright, so W going down, so let's draw W. Okay, now from here, now we'll take one side, T. Actually, let me just draw the original picture first, just to make it a little bit clearer. So the original picture is T, the angle is A, and the weight of the picture is going down. So we have these 3 lines. So when we draw the triangle, we need to make sure that we have one side of a triangle for each of these line of forces. So we'll start with W. Next, let's take this one so that we can continue our triangle. Okay, and our angle, remember, is A. So this is our angle here, A. Now let's take this other side and put it here. Continue. And here we also have angle of A. Here the angle would be 2A. So W, T, and T. Alright, and the next one is also similar. That last one with the boat is similar, except just in a slightly different direction. So what you have is R and T. So water resistance. So once again, we draw one side first, water resistance, that being R. And then let's take T. And again, T. And if we look at the angle that is given, this time the angle that's given is This one here. Yes. Okay, be careful with the angles. Yeah, make sure you're using the right angles. I mean the correct angles for the question. Okay, so that's how you draw a triangle of forces. Okay, you make sure that all the arrows continue from one another. Bukan, you'll never have two arrows pointing in the same direction like that. So for this one, okay, same concept here. All right, it's the same idea except in the form of a pulley. You can clearly see the lines. So let's go straight to solving problems involving forces of equilibrium. Now, even though the textbook shows the solution, right, I still want to go through the solution with all of you. And because and if you have any questions while I'm doing the solution, you can go ahead and ask. And yeah, so let's read the question first. So figure 1.26 shows a stationary lamp hanging from two strings. The tension T is N and the string is inclined at an angle of 60 degrees above the horizontal as shown in the diagram. So the questions are: A, calculate the magnitude of tension P and the weight of the lamp. So basically we are asked to find the value of P and the value of W. So if we look at the question, wait a minute, yeah. So for a question like this, let me go ahead and there you go. So for this kind of question, where you have, if we would draw a simple diagram, 8 newtons, we have P, and we have W, and we have a right angle. So if these two lines are at a right angle, then one solution that we could do is basically to create or use resolution of force as a way for us to solve this question. What do I mean resolution of force? We take this force here and we find this, and we know that this one and this one will be equal to this one and this one. So if we were to do it like that, we will just resolve it. So T, and we know this is 60 degrees. So if we just use the resolution of force method, we'll take T. We have Ty and Tx. And so we know that Tx equals cos 60. Okay, someone's coming in. T cos 60. So which is 8 cos 60. Wait, that's not correct. Oh, here. Yeah, that's right. Yeah, 8 cos 60, which is 4 newtons. So, where was I? So that is P. So therefore, P equals 4 newtons. Ty equals T sin 60, which equals 6.93 newtons. Okay, and so from there we can state that P, for A, P equals 4 newtons, and for B, that W, or the weight of the lamp, is 6.39 newtons. It's a little bit messy right now on the whiteboard. Okay, did you get that, or am I going too fast for you? Setakat ini boleh faham ataupun terlampau cepat saya explain? Okay. Well, one person says, okay, what about the rest of you? Okay. That was all right. Okay. Okay. Anyway, if you have any questions, just say, "Sir, you're going too fast. Please repeat that." I'll be perfectly happy to repeat that for you. Okay, so basically kita aplikasikan apa yang kita belajar dalam resolution of forces to find the other sides. All right. So let's look at example number 2. The other method that you can do is to do a scale drawing lah. The other method is if you had a protractor and a ruler, do a scale drawing and just draw it with all the correct angles lah. So you so you measure 8. Let's say 1 Newton equals 1 cm. So you do 8 centimeters. And just make sure that you have the correct angles for everything. Yeah, you can do that. Of course, I'm not going to do that because I didn't measure it properly, but you can do that. You can also use a scale drawing. Okay, and you should also practice doing scale drawing because the test question might require you to use a scale drawing. So yeah, here's the solution here in the textbook, like what I said, and here's an example of using a scale drawing where you just draw everything properly. So here's example 2. So let's take a look at the picture first. So you have a box. You have a box that's on a slope at a 40-degree angle. And so you can see there's the weight of the box, and there's R, or the normal reaction force, and there's the frictional force. So R, the reaction force, and frictional force is perpendicular and parallel to the slope, whereas W is going straight down to the ground. Okay, so the two questions are, first, draw a free body diagram showing the weight of the box, normal reaction, R, and frictional force. So free body diagram, we've done this before. You just need to draw the lines. Very simple. You don't even need to draw the box itself. So weight of the box is W going down. Frictional force is going this way. And reactional force is going this way, roughly. And with a 90-degree angle between frictional force and normal reaction force, plus at an incline of 40 degrees. But you don't even need to write that in. You just need to write this. And if you wanted to write down the values, well, the only values given is that weight equals 50 newtons. So that's the only value that's given in the question. Okay? So for question B, by drawing a scaled triangle of forces diagram. So question B is asking you to do a scale diagram. So sometimes, like this example, the question will ask you to use the scale diagram method. So if the question asks you to do that, and then that's what you have to do lah. All right. So C is again using the resolution of force method. Right. So by resolving the weight of the box W into a component parallel to the inclined plane and a component perpendicular to the inclined plane, determine the magnitude of the normal reaction R and the frictional force Fr. So sometimes the question gives you a long thing like that. When it says perpendicular to the inclined plane and horizontal, meaning to say in line with this here. So we'll take W. We resolve it into the horizontal and the vertical. Most of you have done this already. Right, so 50 newtons. We have the angle here being 60. And we have Wx and Wy. Okay, so very basic. We've done this before. Wx equals, this time we'll be using sin. So 50 sin 60 degrees, which is where was I? Which is 30. Is it 60? Did I do it wrong? Wait. Oh, sorry, it's not 60, it's 40. It's 40 in the picture. Sorry about that. Anyway, so 50 sin 40. So 32.14 newtons. Wy equals same thing, 50 cos 40, which equals to 32.14 newtons. All right. And by looking at the picture, we can compare, right? So R must equal Wy. Sorry, yeah, Wy, which equals 32.14. And Fr, or reaction frictional force, equals Fx. How do we know they're equal? Remember, it's an equilibrium, meaning to say they have to be equal to each other to produce zero. Equal to each other, just opposite directions. So, wait, I wrote that wrong again. This one is 38, sorry. So 38, sorry, 38.30 and 32.14 newtons. Now, if you look at the question, by the way, let's go back to that question there. You notice that, okay, for this one, it does say stationary. Okay. So in this question, it does say stationary. So yes, we know the resultant force is zero. I saw another question. I forgot which question was it. Where it doesn't say stationary, but it says the box is sliding down at a uniform speed. Okay, if you hear that question or if you see that question, the resultant force is still zero, because remember, an object that is moving at a constant speed is also in a state of equilibrium. All right, so far example 1 and example 2 are basically similar to things that we have already done, just that we're using it to find an equivalent force in the triangle. Now, so yeah, the solution is already given here. Now, example 3 is the one that's a little bit more interesting, because now we have to use a different formula. It's a little bit longer, so pay attention. So first we need to draw the triangle. Okay, so figure 1.30 shows a poster hanging on the wall of the laboratory with a string and a nail. The weight of the poster is 12 newtons. So two questions are: draw the triangle of forces for the weight of the poster and the tensions in the strings, and B, calculate the value of T. So we look at the picture. This is like one of the examples we did earlier. So we'll start with drawing W. Normally I like to draw W first, because usually it's a straight line going down. If there's any question that involves weight, I try to start with any straight lines. That's either straight vertical or straight horizontal. That just makes it easier for me. So W, which is straight down. Okay, next we can take T. We can take either side, either the lefty or the righty. I'm going to start with the lefty. Okay, so following the direction of that side, we have T, and this is 35 degrees. And continuing to the last side, again we have T, and another 35 degrees here, which means here the angle here is 70 degrees. Which means this, and since it's on equal sides, then this and this angle is the same, so 55. Now, you don't have to write in every single angle, just the main ones. The main one would just be these two. But these other angles will be useful later when we try to solve the question. Now, the first thing that you notice is none of the angles are right angles. We don't have any 90-degree angles, which means we cannot simply use Pythagoras theorem to solve this. Yes, yes, exactly, Henry. Well, it's right there in in the textbooks. You can either use the sine rule or the cosine rule. Right? So sine rule. Well, let's go ahead first with the first question. So first question, we already have triangle of forces. So we already have drawn the triangle of forces. So now we need to calculate the value of t. So the text, well, there's three methods. Method one is to do a scale drawing. Then just take a protractor, take a ruler, and make sure you measure everything correctly. But even the textbooks say that using a scale drawing is not going to be as accurate as calculating. But you can get a rough idea using a scale drawing. Normally, a scale drawing, what you would do is you'd calculate first using some of the mathematical formula that you have learned. Then you can use a scale drawing to check your answer. If your scale drawing and your calculation is almost the same, but maybe different by 1 or 2, then you can assume that your calculation should be pretty accurate. Now, if your scale drawing and your calculation there's a difference of like 10 or 50 or 100, then probably there's a mistake either in your scale drawing or most likely your calculations. Okay, so I'm going to show you both methods now, the other two methods. So either you use the sine rule or the cosine rule. So if you don't remember what the sine rule is, according to sine rule, well, let me help you review what is the sine rule. If we take a triangle with three sides, we have angle A, angle B, and angle C. Wait, let me draw that nicer. B, A, and C. And the opposite side, the side opposite to the angle, we'll call this side B, small letter. We have side A and side C, small letter. How do I make a big letter C look like a big letter C? Alright. Then the sine rule says that sin A over A equals sin B over B equals sin C over C. That is the sine rule. And we use sine rule, to either find a side or to find an angle. You've learned this already in maths. Now the other option is to use cosine. So cosine rule, if we use the same triangle, cosine rule is normally in physics the one we use is A square equals B square plus C square minus 2BC. Is it sin or cos? Sorry. Cos A. Let me write that again to make it neater. Cosine rule would be A square equals B square plus C square minus 2BC cos A. Okay, so either one of these two formulas are possible. Okay, and you will have to answer depending on what information that is available in the triangle. Okay, you might have a question where only the cosine is possible, or you might have a question where only the sine rule is possible. So sine rule is if you have three sides, you can use it if you have like two sides and the opposite angles, or if you have all three angles, or if you have like one side and three angles. or 3 sides and 1 angle, you can use sine rule. If you only have 2 angles, if you only have two sides, and 1 angle, then you can use cosine. Go and review. You can go and review that in your is it maths or ed maths? I forgot. Right? Just go. You've learned that before. Go ahead and review that. So back to the triangle just now. So back to that triangle that we drew earlier. So W, T, and T. And we know that this is 70, 55, and 55. So let's try first using the sine rule. We know that W equals 12. So let's put down 12 here. So, method 1. Using the sine rule. Alright. So, according to the sine rule, we have we have one side that we already know and one angle that we already know. So W over sin 70, these two sides, is definitely equal to T over sin 55. Yeah, from there it's a simple calculation. Therefore, T equals 12, because W equals 12, sin 55 over sin 70, which in your mathematics, which in your textbooks and in my calculations last night equals 10.46 newtons. The other method is for you to use the cosine rule. So when I tried using the cosine rule last night, I actually managed to find a different way. I didn't find. I actually did it a different way. Which, by the way, I recommend all of you to try and do the examples on your own. Even though the textbook also does the answer, you can go ahead and look at the answer to see how it's done. Then close the answer and then try the question for yourself. That you can learn a lot by doing that. So, method 2 is by using the cosine rule. So what the textbook does is, well, let's do it how I did it first. The way I did it would be, I wanted to find T. So T equals, or rather T square equals, so I assume that the other T is on this side. And then we have W. So T square plus W square minus 2TW, right? Cos, so the angle that's opposite to T is 55. So 55. And so what I did was, this T, I move it over to this side, so we get 0. 0 equals 144, because W equals 12. 12 square is 144. Minus 2. Well, 2 times T is still 2T. W equals 12, so 24T. 24T cos 55. Now from here, I did 24T cos 55 equals 144. T cos 55 equals 6, because 144 divided by 6 equals 6. Sorry, 144 divided by 24 equals 6. Then T equals 6 divided by cos 55, which equals 55, which equals the same answer, which is 10.46 newtons. So that's how I did it. I did it by making t using the side t. Now the way a textbook, my way is a little bit longer actually. The way your textbook does it, I'm going to show you how the textbook does it. And it's still correct. It's not wrong. It actually uses W. So by using W, it does W square equals T square plus T square minus, so 2T and T. So basically T times T times cos 70. Cos 70. Excuse me. So W square. So in other words, 12 square. So 144 equals T square. And it actually simplifies it by doing it. 1 plus 1 minus 2. But so what it does, it actually factorizes it. Cos 70. And therefore, T square equals 144. 1 plus 1 minus 2 cos 70. And therefore, T equals 10.46. So the textbook actually does a different way, but both ways are using the cosine rule. It really doesn't matter as long as you arrange it properly. All the numbers and all the factors incorrectly, you still should end up with the same answer. All right. So, okay. Any questions before we try some questions together? No questions? Okay, so if you have no questions, then go ahead and do formative practice 1.3. If you have your textbooks, then you should be able to see it. Let me just zoom out a little bit. So go ahead and try to do formative practice 1.3 and go ahead and do question number 2. Okay? And go ahead and try to tell me the actually. All right, so the question doesn't ask you to do it, but I want you to go ahead and find the value of, well, it doesn't show it, does it? All right, never mind. It doesn't ask you to show. Okay. Here's what we're going to do then. We have 30 minutes. And if there are no questions, we will end this Google Meet, and I'm gonna send you a question to do. Let me just have it here somewhere. Okay, here's what I'm going to do. So I'm going to send you a worksheet for you to do. I want you to do question number 1 by today, before this class ends in the first 30 minutes. Question number 2 and question number 3, you can do that as your homework. So you can do that later. But I want you to do number 1 first together so that I can give you immediate feedback on how you did it. All right? Any questions? If there are no questions, then I will dismiss you for today. Oh. Okay. All right. Yeah, you missed the first part. So the first part is we talk about how to create a triangle of force. Okay. Actually, actually, let me just go through that very quickly. Let's go through that very quickly for Davy. So what we were talking about earlier was forces in equilibrium. So forces in equilibrium is when the resultant force equals 0, meaning to say when you add the vertical and horizontal and your result is 0 overall, then that's what we call an object in equilibrium or a state of equilibrium. So all the questions and all the examples that we did just now are assuming that the forces are in equilibrium. So here's an example of something that's in equilibrium. This vase sitting on a table, the weight of the vase is 12 newtons. However, the reaction, normal reaction on the vase is also 12 newtons up. So 12 minus 12 equals 0. So the resultant force is 0, meaning to say it is in equilibrium. If you have three forces like this, then what you have to do is to draw it into a triangle like this. And this triangle actually shows that it is still in equilibrium. How does it show? Once again, I'll repeat this very quickly. And for everyone else, okay, let me draw it. So if we take this original diagram up here, what I usually do is I either take the vertical line or the horizontal line, whichever line is the straightest. That's the easiest for me to start with. So I'll start with W. The line is going down, right? Now, from here, what I do is, when you're drawing this triangle, you should only move in one direction. What I mean is you do this, then you do this, then you do this. You don't repeat directions. You don't do this. You don't do this, and then you do this, and all of a sudden you do this. Don't repeat. This would be wrong. In a triangle of forces, or you should always continue the direction. Alright, anyway. So back to that first diagram that we had. So we start with W, and then we will draw P. So W, P, and T. So all the forces in the triangle make up a, all the three forces make up a triangle like this. So how is it possible that three forces like this still end up with a resultant force of 0? Because W, okay, if we take T and we resolve it into a vertical and horizontal force, so let's do Ty and Tx, you notice that the direction is exactly opposite to the force that we have already in the diagram just now. So Ty is exactly opposite of W, Tx is exactly opposite of P. That's how one line can actually cancel out two other lines. So every single question that we did earlier is based on that triangle of forces. So as long as you know how to draw a triangle of force, you'll be able to draw. Once you draw your triangle of forces correctly, the rest of it is a matter of just calculating everything. So here are some other examples lah. Alright. Okay, is that okay for you, Davy? Nanti tengok balik lah di YouTube. Okay, how about the rest of you? Fine? Alright, so since there are no other questions, so let's just quickly take